The only other derived quantity I want to comment on at this time is density. I hope you watched that video that I made in which I show how I can suspend an egg in between two liquids. And what was going on there is the egg was sitting right here at the boundary of the two liquids. The top liquid being water with a density equal to 1 gram per milliliter. And I made a concentrated solution of salt in water, which has a density greater than 1. And again, the reason why the salt water has a density greater than 1 is because there's more mass crammed into the same volume. For equal volumes of solution or liquid in salt water, you have simply more atoms, more ions floating around, so it simply is more dense, just like a city like New York is more densely populated than a city like Appleton. For every square mile, there are more people in New York City than there are in Appleton. So New York is more dense. That's how matter works as well. More dense matter is simply more grams per milliliter for the same volume. So it's a very simple formula. Density equals mass per volume, or mass equals density times volume, or volume equals mass over density. You can use any of these formulas to either calculate the density or the mass of a liquid or the volume of a liquid. So density relates grams to milliliter. We can actually weigh a liquid by measuring its volume. So remember, in the video I showed this slide where I explained why the salt water was sinking. So I hope that's pretty clear to you guys. The salty water just has the additional sodium chloride. I say they're molecules, but they're actually this is what it would look like on a microscopic scale. There'd be ions of sodium and chloride floating around with the water molecules. So it's obviously going to be more dense. And also, as I commented on, temperature affects the density. So a cold liquid will always sink in a hot liquid. So as you add heat to the cold liquid, the molecules of water, let's say it's water, the molecules of water start moving faster. If they're moving faster, they're going to take up more space. Therefore, they're going to take up more volume. So if the volume increases as a liquid gets heated up, this number in the denominator increases. So a hot liquid has a higher volume, and since volume is in the denominator, density is going to go down. It's going to decrease, because the relationship between volume and density is what we call an inverse relationship. An inverse relationship is one in which one variable would go up, the other one would go down. So as volume increases, density decreases. As volume decreases, density increases. So as you cool the hot liquid back down, the volume will then decrease as the molecules of water slow down. They occupy a lower volume. This number decreases, therefore the density increases. And again, that is how ocean currents and work. Sort of the hot water and the cold water currents are kind of overlapping each other, and that influences weather and things like that. So please watch the video as well if you haven't already. It's on Canvas, where I show you a demonstration of density. And just to give you an idea of how what different objects, the densities of different objects relate to each other. If you looked at gases versus liquids versus solids, you'd see that, notice these are all in units of grams per cubic centimeter or grams per milliliter. And remember, I've said this many times, the units of grams per cubic centimeter are identical to grams per milliliter. So you can use either one. It's just common practice that we use grams per cubic centimeter to express the density of a solid, because a solid is three-dimensional. We measure its length, width, and height in length. Centimeters is a convenient unit, but we could express it in grams per meters cubed if we wanted to. And liquids is usually expressed in grams per milliliter, but you can use either one and you'd be right. Notice that the density of gases is very low, and the density of some solids is rather high. For instance, helium will float in air. So we've all used helium balloons. The reason why they always fly away up into the, if you let them go, they're going to fly away into the sky, because the density of helium is lower than air. So helium balloons experience a buoyancy effect and get pushed up into the air. Eventually, helium, you might notice if you have a helium balloon at home, it'll eventually sink to the floor. That's because there's diffusion going through the balloon. Helium atoms are escaping and air is moving in. So eventually, given enough time, the helium escapes and is replaced by air. So the density of the gas inside the balloon becomes the same as the air around it, so it sinks to the floor. Now, liquids like water, everything is defined in terms of density relative to water. We say water is 1 gram per milliliter. But remember, that's a made-up convention. We only defined it to be 1. So we based all our scales and our balances on that. So water, since we use water so much, we just called it 1. We could have chosen any liquid to be the base reference unit, but water is the most common one, so we chose that. Blood plasma and urine are slightly more concentrated or dense than water because they have salts and other things dissolved in them, just as I showed you in the video on the salty water. Ice has a density of 0.917. Now that's interesting because ice floats on water because its density is less than 1. For almost all other liquids that I know of, the density of the solid phase of the liquid is always denser. So as a liquid freezes, for everything besides water, the solid sinks in the liquid. But that's just a happy coincidence for us because since ice floats, the life inside the lake or the ocean, whatever is freezing, will be able to survive underneath the ice. If water behaved like most substances and froze from the bottom up, it would be very difficult for the sea life to survive every winter. Gold, you can imagine, is very dense. It's almost 20 times denser than water. That's why if you've ever held a piece of gold in your hand, it feels very heavy. Human fat and oils and things like that are always less dense than 1, so they float on water. Cork, of course, floats on water, so that's density is less than 1. Table sugar is a solid, so that would have a density greater than 1. Balsa wood floats on water, density less than 1. And earth, dirt, and things like that, very dense. A lot of mass packed into a unit volume is greater than 1. So I hope that helps clarify what density is a little bit. We'll use this for some calculations in lab, and it's a physical intensive property of materials that is used all the time in this class. So now that you know a little bit about all the units we're going to use in this class, let's talk about measuring liquids and solids and gases in labs, because measurements are the only way we can quantify something that we're carrying out in a lab or in research. So I noticed in lab this last week, most of you were reading the glassware correctly, so that's great, but I think we all still need to practice a little bit and make sure that we're reading this glassware correctly. So remember, every experimental measurement has a degree of uncertainty. It's going to be in the last digit that you express to the right. That's your uncertain digit. That's what we call an estimate. So let's just look at these examples. Again, I don't know if I've shown you this before. I gave you these in that handout I passed out in lab. But so if you look at a burette, close up at a burette reads volume increasing downwards. So you have to always remember that, because a lot of people would initially look at this, and I've even made the same mistake where I think it's over 7 milliliters, but it's a burette. I know this is a burette because it's increasing down. 7 is below 6. So remember, most of the liquids we use in this class are water-based. So water-based solutions will form this curved meniscus upward inside a glass tube. And that's because water is attracted to glass. Water will pull itself up the glass and leave this curved surface. The degree of curvature is a function of the diameter of the tube. So the thinner the tube, the more curved the meniscus will be. You might have noticed that when you looked at the meniscus inside the burette. It was a lot more of a curve than a meniscus inside the wider graduated cylinder. For instance, that 1000 graduated cylinder that you used to measure the volume of the egg by dropping the egg into water, that looked like a flat meniscus. So this is kind of exaggerated even for a 50 milliliter graduated cylinder. It isn't really that curved, but this is only for illustration purposes. But if you look carefully, And it would help to put your hand behind the glassware so you can see this dark line. You actually can see it if you look carefully. You have to be at eye level to read a meniscus properly. So this would be a volume of 6.6. Those are what we call the certain digits. But if you look carefully, this volume of liquid is a little bit below the sixth line after 6. So we would say a reasonable estimate of volume would be 6.63 milliliters. But if somebody said it was 6.62 milliliters, that would be acceptable as well, because again, there's usually a plus or minus 1 of uncertainty in the last digit. So anything between 6.62 to 6.64 milliliters would probably be acceptable, even though you can probably see that it looks more reasonable to say it's 6.62 or 6.63. But we usually accept an uncertainty of plus or minus 1 or low, or 1 plus or minus 1 high in the last decimal place. So this goes for any measuring device. So in a 50 mil graduated cylinder, if you look at the meniscus here and you look at how many little divisions are in between 40 and 50, you'll notice that there are 10. So each of these little marks corresponds to 1 milliliter. So if I'm reading the liquid and it makes a meniscus like this would be 41, that would be 42, 43, 44. I know it's at least 44, but not 45. So it's not good enough to just say, oh, it's about 44. You have to be specific. So the uncertain digit is always going to be 1 decimal place to the right of the smallest mark on the piece of glassware. So since this is 1 milliliter, which is the ones place, there's always an uncertainty in the tenths place. In the burette, the small little mark here, if you look carefully, there are 10 marks in between 1 milliliter. Therefore, each of those lines stands for 0.1 milliliters. So therefore, I can estimate to the hundredths, the second decimal place, I can estimate to the hundredth of a milliliter. So that's why this has more decimal places than this. So we say the burette is a more precise piece of glassware than a 50 milliliter graduated cylinder. So, but I still get 3 sig figs in this measurement as I do here. So that the other part of this chapter we're talking about is not only how you should properly make measurements, but you should also be able to keep track of the significant figures. The significant figures simply mean all the important numbers that go into a measurement that all have meaning. So a reasonable estimate for this volume could be anything between 44.7 to 44.9 milliliters. Those would all be acceptable answers. Now, if you're using something like a simple ruler, this is a pretty crude ruler. It doesn't have any divisions other than 1 mark in between any 2 numbers. So if I'm reading this ruler correctly, and this pencil is stopping right here, the end of it is right here, exactly on that line, all I can say is the length of this ruler is 7.5. I can't say 7.41. I cannot say 7.52. I can only say 7.5, and that's it. So that would have 2 significant figures. If you look at a thermometer, thermometers that have more marks on them are going to be more precise. So if you look carefully at this thermometer, it doesn't have any marks in between any of these, which are called, well, they're degrees. So this is 21, 22, 23, 24, etc. So let's assume this is reading temperature in degrees Celsius. How would you properly read? And this pinkish liquid is the alcohol or the mercury in the thermometer. So this temperature would read 21.2 degrees C. I say that because to me it looks like this liquid is about 1/5 of the way from here to here. So I'm calling it 21.2. Somebody else might say 21.3, and that would be fine. If the mercury or the alcohol inside the thermometer is right on a line, I have to still indicate that it's on a line by putting a 0 in. So this temperature would be 22.0 degrees Celsius, and that's it. You have to put the 0 there. That has 3 sig figs, that has 3 sig figs. So a thermometer calibrated like this or marked like this with 1 degree increments has to have 1/10 of a degree as the last uncertain decimal place. And finally, to illustrate this, let's say we have a much more precise thermometer. So not only does it have 1 degree markings on it, but in between each one mark, I think you can see this in the video, there are 10 little marks in between every 1 degree. So every one of those little marks is 1/10 of a degree. So a reasonable temperature, I could read from this liquid is just above the first line past this second line. So I would read that as 22 point, it's at least 22, and it's just past the first line, so I know it's at least 22.1, and it looks like it's barely past the first line, so I'll say 22.11 degrees C. Another reasonable temperature would be 22.12 degrees Celsius. Those would both be correct, but I can get 4 significant figures out of this one. Here are some measurements that you might have in a laboratory. So it's very important that you can read or tell us the number of significant figures. I'll sometimes call them significant digits as well. I just call them sig figs. It's easier to say, as a lot of us do. So 6.63, they're all non-zero digits, so they all count in the measurement. 3 sig figs. 44.8 milliliters, 3 sig figs. And notice, on every measurement that we make, you have to have a unit. Otherwise, the number is simply meaningless. 22.11, they all count. 1, 2, 3, 4, 4 sig figs. 54.07, 4 sig figs. Now, that would be recorded on a balance like you used in lab. The ones you used in lab actually are precise to 3 decimal places, so they're pretty good. But there's even a more precise balance called an analytical balance. So if we put the same object on one balance, like what's called a top-loading balance that's usually found in every lab, might read 54.07. That 0 counts as being significant because it's trapped between 2 non-zero digits, so that has 4 sig figs. But if you put it on another balance, it might read 54.0714 grams. So that would have 6 sig figs. So this balance here can only tell us to the second decimal place. There's actually more mass that is there, but it is not. This balance wouldn't round it up to 54.08 because this number here after the 7 is less than 5. So devices are calibrated that way to do that, to round off to the last decimal place. But that, again, this is just what we say is a more precise mass. So since the hardest part of all this seems to be how we treat zeros in measurements. So when you're reading a measured value, all the non-zero digits are counted as being significant. There's a set of rules that we use for determining if a zero is not significant or not, is significant or not. So here's rule 1. Rule 1, I'll just show you with numbers. Zeros in the middle of a number are like any other digit, so they're always significant. So for instance, the mass 94.072 grams would have 5 sig figs in it. They all count. The zeros trapped between non-zero digits, so it counts 1, 2, 3, 4, 5 sig figs. And again, you might be wondering, why do we care so much about how many sig figs there are in a measurement? Because we often use measurements like this, like mass. We might be using it to calculate the density of an object, just like you did in the density you're doing this week in figuring out the density of an egg. The density that you calculate, or if you use mass in some other formula, you have to keep track of sig figs for each measurement, because that's going to influence how many sig figs and how precise you can say your final answer is. You can't just say your final answer has 10 sig figs in it, like a calculator might spit out a number. A calculator doesn't know how to round off numbers. It's just a simple computer. So we have to round off numbers that we calculate. Rule number 2 is zeros at the beginning of a number are not significant. They only act as a placeholder. So for instance, if you put something on an analytical balance or measured something with a very precise ruler, and let's say it was really small like that, 0.0834 centimeters, that would only have 3 significant figures. The zeros don't count. So leading zeros, I sometimes call them. You would call these leading zeros. They don't count. So that would only have 3 sig figs. Just like number like a measurement like 0.29 0.02907 milliliters would have 4 significant figures. Now, it's hard to find a device that would have that many, give you that amount of precision with a milliliter, but again, I'm just trying to illustrate the rules to you. I kind of made these up. Rule 3 is zeros at the end of a number and after the decimal place are significant. So it's assumed that these zeros, we wouldn't show them unless they were significant. So let's say you measured the length of an object with a ruler or some device that allowed you to get 3 decimal places, and it was right on a second mark, let's say after the 8. So you'd have to say there's 2 more zeros there. Let's say that's meters. So that number, since the zeros are after a decimal place, they are put there for a reason. They are significant. So this would have 6 sig figs in the measurement. And the last rule, Rule 4, is zeros at the end of a number and before an implied decimal point place. When I mean implied, I mean sometimes we write a number, a really big number, but we don't put a decimal place. So it's implied to be after the last digit on the right, of course. So zeros at the end of a number like that, and before the implied decimal place, they may or may not be significant. We can't tell whether they're part of the measurement or they only act to locate the decimal place. So in this class, I'm going to say if there's no decimal place and there's zeros before it, just assume that those zeros don't count. So the number 1,000, let's say meters, for instance, was measured with a device that was only allowed us to give us 1,000, 2,000, 3,000. We would say that would only have 1 sig fig in the answer, in the measurement. Those zeros don't count. And the reason is, you'll see in a little bit when I talk about what's called scientific notation. I can express this number in scientific notation and not include the zeros at all. So it only has 1 sig fig. So if I change that to the number 1,000 with a decimal place, now that zero is kind of like this zero here. It's put there for a reason, and the decimal place tells me that the zeros are significant. So whatever device, let's say it's meters again. So maybe I used a measuring device that allowed me to get exactly the units of a meter, the units place. It was just calibrated with more precision or marked with more precision. Therefore, this number would have 4 sig figs. See, just putting the decimal place there changes it from 1 sig figs, those aren't significant, to putting it there makes those zeros significant. So that's the rule I want you to use in this class as well. So let's continue our discussion of numbers and measurement. Some numbers, unlike measurements, are exact. So there's 2 types of exact numbers, and keep in mind that exact numbers have an infinite number of significant figures. That essentially means we're saying there is no uncertainty in the measurement. There's 2 types. There's counted items, so I can count in a room there's 22 students. There is no uncertainty in that. There's not 21.5 students. There's not 22.3 students. There's 22 students. In a stadium like Lambeau Field, there might be around 78,351 seats. No uncertainty. That is a counted item. These have no impact on the number of sig figs in the final answer if they're used in a calculation. That's the point. Accepted definitions are the other type of exact number. So things like 1 mile is 5,280 feet, 1 hour is 60 minutes, 1 year is 365 days, 1 pound is 16 ounces. These are all definitions we made up, but we know them to be true. There's no uncertainty in them. So for instance, if you did a calculation where somebody said asked you how many feet are in 3 miles, you just plug into your calculator or add it up. 5,280 times 3 is 15,840. You would not round that off. When you use digits that have been measured, you have to round off the final answer. I could write this answer as 15,840.000000, an infinite number of zeros, and I would be just as correct as saying 15,840. I could put all those zeros in. I don't need to, but that's what that means. There's not any uncertainty in that. So keep that in mind, please, when you're doing calculations in this course. Now, the other thing I want to clarify is a lot of people seem to confuse accuracy versus precision. A lot of people use them in the inverse way, or they they think they're the same thing, but they're not the same thing, at least in science class. A measurement is considered precise if it yields a very similar result when you repeat it many times. So if I gave a graduated cylinder with some liquid in it, and I gave it to 4 different people, one person might say it's 32.5 milliliters, another might say 32.4, another one might say 32.5, and the fourth might say 32.6 milliliters. But they all are precise. They all have the same number 32, and they're only different in the last decimal place, the last sig fig, either plus or minus 2. So that's a very close range. So we say those are precise measurements. Compare that to a measurement that we say is accurate. A measurement that's accurate means it yields a result that's very close to the true or accepted value. So we know that a nickel, 5 cents, weighs pretty much exactly 5 grams. They make them that way. Let's say I put a nickel on a balance. I'm testing to see if the balance is working properly. If I put it on balance 1, for instance, and the mass of the nickel is 4.99 grams, I would say that balance is accurate. It's pretty darn close to 5 grams. If I put the same nickel on a different balance, but the balance says 5.37 grams, I would say that balance is not accurate. It needs some calibration. I wouldn't use that balance. It's not giving me a reliable result. So another way to illustrate or understand the difference between accuracy and precision might be a series of a bunch of data that somebody acquires. Let's say they work for a company that makes 10-ounce dispensers, which is 296 milliliters, and they have to make sure that they're delivering 296 milliliters accurately. Whoever buys them wants to know that they are accurate, especially when you're dealing with medicine. You have to deliver very precise and accurate amounts to be safe. So let's say they make 3 different dispensers, or they're buying them from 3 different suppliers. One dispenser, we'll call it dispenser number 1. They measure the medicine 5 different times. It gives them 283.3 one time, 284.1 the next, 283.9 the third, 284.0, 284.1. So you can see that they're all kind of close together, but they're not really close to 296 milliliters. So we would say that these measurements are precise, they're close together, but they're not accurate. Compare that to a dispenser that might give you more accuracy, but it's less precise. So these are closer to 296 mils. They did the same dispensers 5 times. They measured the 10 ounces 5 times. One gave 298.3, 294.2, 296.0, 297.8, and 293.9. You can see there's a much higher range of volumes measured versus this. It almost is, of just looking at it here, it goes almost about it's over 4 milliliters from low to high, whereas this one was plus or minus maybe 0.2 of a milliliter, maybe not quite 1 milliliter difference between the low and high reading. So this second dispenser is closer, more accurate, but it's less precise than dispenser number 1. They'd be looking for a dispenser like this. The best dispenser would be one that gives you repeatable volumes, and they're close to 296 milliliters. So you can clearly see that this third dispenser is very close to 296. It's only off by 1/10 of a milliliter. That's pretty good. And it's close to the accepted value of 296. So we'd say that those measurements are precise and accurate. Now in this class, we're going to deal with very small numbers and very large numbers. So it's very important that you can use and write numbers in scientific or exponential notation. So if you haven't already done so, please watch the Powers of 10 video I put a link to on Canvas. It is a good demonstration of the power of 10 and between the very large and the very small. It's fun to watch. And also there's a couple pages in the back of the textbook in Appendix 8.1 on pages 1051 and 1052 where it goes over a lot of the rules that I will show you here. So we write numbers in scientific notation because it's just easier to write a really large or really small number this way, and so we don't have to write all those zeros. So let me just give you a series of examples. So let's say we know the US population at least a couple of years ago, I think if I had to guess what the US population is, it's probably 340 million people. So let's say we took the census was this year, I believe. Let's say they came up with 347,500 or 347,500,000 people. All right. You could write that number in scientific notation like this. You write it as a number between 1 and 10, and you don't include any zeros that aren't significant. So these are only placeholders, they're not significant. So the 3, the 4, the 7, and the 5 are significant. So I could write it as 3.475, and then multiply it by a number, a power of 10. And it would be, you imagine that the decimal place is here, and then you count the number of places you have to move to put the decimal at the proper place. So we know that there's an implied decimal place here. So I just count from here, 1, 2, 3, 4, 5, 6, 7, 8. So I could write that number as 3.475 times 10 to the 8th people. And it's as simple as that. You can also use it for very small numbers as well. So let's say I measured something on a electron microscope, and it was very, very small, 0.00000000372 meters. So that's kind of inconvenient, right? It takes a while to write that. So, and also to enter in a calculator, your calculator may not even be able to handle all those digits, but it certainly can handle a number written in scientific notation or typed in scientific notation. So here's the real decimal place. We imagine the decimal place to be here between the 3 and the 7, because I always want to write a number. When I write it in scientific notation, I want to write it as a number between 1 and 10, and then multiply by a power of 10 that actually locates the decimal correctly, which is here. So now here, in this example, I was moving to the right, so my power of 10 is greater than 1. If I have to move the decimal that I'm applied decimal, or I'm sorry, the decimal I'm making up, if I have to move it to the left, to the real decimal place, the power of 10 is negative. So it's 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the negative 9th meters. And the nice thing again about scientific notation is that it shows me exactly how many significant figures are in my measurement. Here in this population measurement or counting, I would have 4. And remember, I said count. When you count things, it has an infinite number of sig figs. But in a census of the United States, we really never know the true number, because a lot of people don't answer the census, or they just round it off and give us an approximate number. So if they rounded it off, it technically would have only 4 significant digits. If we measured this length of an atom or something under a microscope, this actually is a measurement, so we have to include sig figs, which are only the 3, the 7, and the 2. So that's why this number here only shows 3 sig figs as well. So if you're not sure or comfortable with this, please, you'll need to review this with and make sure you can, and you're going to make, it's very important you can actually enter these numbers in your calculator. So if you're good at this, you could probably fast forward a little bit, but those who are still struggling a little bit, it's very easy on my calculator to enter a number in scientific notation. If I wanted to enter this number in scientific notation, all I would need to do on this particular model is enter 3.475, and then I would type in EE, and then the little double 0 pops up, and then I just enter 8. Now if I hit equals, this might have enough zeros to display it, which it does. It actually converts it to 347,500,000. If you want to go back to scientific notation from a number you entered this way, let's say I enter it 347,500,000, and I want to enter that or write it as scientific notation using the calculator. On this one, I go the second function of the key, the 5 key, puts it in scientific notation like that. Same goes for very small numbers. So if I enter this number here, I don't think I can enter that in scientific notation or standard notation. So in scientific notation, you just enter 3.72 EE. It's a -9, so I hit -9, and you should see a little, I think you can see that on the camera. So that's a very, very small number. If you want to go from a number written in scientific notation back to standard notation, you just do the opposite of what I said. So let's say you have the number 3.7962 times 10 to the 4th. How would you write that in standard notation? Multiplying by 10 to the 4th is the same thing as multiplying by 10,000. So that's moving 10 to the right. So I'd write that as 1, 2, 3, 4, which is 37,962. If I see a number like 1.56 times 10 to the -8th, and I want to write it in standard notation, what I do is, when I know it's a really small number, I always just put a number of zeros. And I learned that there's a little trick. If the number of zeros before the first non-zero digit, when it's a really small number, will always be one less than the power. So if it's -8, I know there'll be 7 zeros. So I write 1, 2, 3, 4, 5, 6, 7. And then I write the 1, the 5, and the 6. And let's just make sure that works. 1.56 times 10 to the -1, -2, -3, -4, -5, -6, -7, -8. So there you go. 7 zeros here, one less than the power. And then let me give you an alternative way to move between standard notation and scientific notation, in case you didn't like the way I explained it the other way. But it's not that much different than what I already said. You can think of the number for 0.00215 as just the number 2.15 divided by 1,000, which I've written like this: 2.15 times 1 over 1,000. Well, you can think of the number 1,000 as 10 times 10 times 10, but it's in the denominator, so we could rewrite 1 over 1,000 as 1 over 10 times 10 times 10. Well, that is just 1 over 10 to the 3rd power. And if you remember your high school arithmetic class, any number with a positive power in the denominator written in the numerator becomes negative. So 10 to the 3rd power in the denominator is 10 to the -3rd power in the numerator. So I could just rewrite this as 2.15 times 10 to the -3. So either way, I just think of it as moving the decimal 3 to the left, so I know the power is going to be negative. It goes for even a large number like 1 million. You can think of it as just 1 times the power of 10 6 times. 10 times 10 times 10 times 10 times 10 times 10, which in your calculator is 10 to the 6th power. So hopefully that's pretty obvious there, but that's just another way of looking at how to express a number in scientific notation. Now, your calculator, when you get answers, does not know how to round them off, so you have to do that. There are 2 general rules. There's multiplication and division, rounding off, and then there's a rule for addition and subtraction. So you have to be able to decide how to do that. So it's pretty simple, though. Multiplication and division is real easy. Let's just say you had to calculate the fuel efficiency of your car, and you filled up at the gas station, and you drove a full tank of gas, and you were able to drive 278 miles. And when you filled up, the gas pump said you filled up 11.70 gallons. What's the fuel efficiency of your car? Well, if you plug it into your calculator, this is what your calculator is going to spit out: 23.76068376 miles per gallon. But you shouldn't keep all those digits. You only had 3 significant digits in your distance and 4 significant digits in your volume of gas. So it's reasonable to think that you can't report more than 3 significant digits in your final answer. So you'd have to round it off to 23.8. I can keep the 2, the 3, and the 7 in my non-rounded answer, but I round the 7 up to an 8 because the first digit after 7 is a 6, which is greater than 5. Now, the exception to the multiplication and addition and division rule, is as you use counted things. So if you had to calculate how many 11 egg cartons held, how many eggs 11 egg cartons held, it would be exactly 132 eggs. You wouldn't round that off to 130 because those have 2 sig figs in them. Remember, those are counted items. There's no uncertainty in that. The other general rule is the addition and subtraction rule. Very easy to illustrate that with this example here. Let's say you took an object and weighted on two different balances. One was more precise than the other. You want to know the total mass of the two. One balance told you 1.5327 grams. The other balance told you 1.54 grams. If you add those two numbers up, you'd get 3.0727 grams, but you'd only be allowed to report 3.07 grams. So you round to 2 decimal places because the number 1.54 only had 2 decimal places. The answer can't have more digits after the decimal than either of the original numbers. So that only had 2. So you have to round it off to 3.07. So to summarize the rounding off rules in this class, here's how we're going to do it. Once you decide how many digits to retain, the rules are this. Rule number 1, if the first digit you remove is 4 or less, drop it, and all the following digits become, or they don't change. So 2.4271 becomes 2.4 if you round to 2 sig figs. If you rounded to 3 sig figs, it would be 2.43. That's using the next rule. Rule number 2, if the first digit removed is 5 or greater, round up by adding 1 to the last digit kept. So 4.5832 becomes 4.6 if you round off to 2 sig figs, because the first number after 5 is greater than 5. If a calculation has several steps, it's best to round off at the end. So in the next video, I'm going to show you some unit conversion problems where I'll illustrate that.